All right. Good morning, good afternoon, and good evening, everyone. Depending on where you are joining us from, and welcome to the third day of the Learning of Graphs conference. I'm Yanqiao Zhu. I'm currently a second-year PhD student at UCLA, and it's my pleasure to be your session chair today. Um, Before we dive into today's exciting agenda, I'd like to take a moment to introduce our keynote speaker for the day, a distinguished figure in the field of machine learning with graphs, Professor Stephanie Jacalda. She's a Humber Professor at Technical University of Munich and an Associate Professor in the Department of ECS at MIT. She's a member of the Computer Science and AI Lab, the Center for Statistics, and an affiliate of IDSS and ORC. Before joining MIT, she was a postdoctoral researcher at UC Berkeley and obtained her PhD from ETH Zurich and the Max Planck Institute for the Intelligent Systems. Stephanie has received a Solon Research Fellowship, an NSF Career Award, and a DARPA Young Faculty Award, an Alexander von Humboldt Professorship, Google Research Awards, a Two Sigma Faculty Research Award, and the German Patent Recognition Award and a Best Paper Award at the International Conference for Machine Learning. She also has been invited as a sectional lecturer at the ICM 2022. She has served as an area chair for NeurIPS and ICML, an action editor for Journal of Machine Learning Research, and as program chair for ICML 2022. Her research interests span the theory and the practice of algorithm machine learning, including learning with graphs, learning with symmetries, robustness to distribution shifts, and learning with limited supervision. So today, Stephanie will be sharing her latest insights with us. I'm sure we are all eager to learn from her expertise and get new perspectives on the challenges and opportunities in learning with symmetries. So if you have any questions during Stephanie's keynote, please feel free to post them in the Slack channel or in the Q&A section in Zoom. So without further ado, please join me in giving a warm welcome to Stephanie.
Thank you for the long introduction and for the invitation to speak here. Sorry. It's a pleasure and an honor to be speaking at this conference. So yeah, in today's talk, I wanted to speak a bit about some things we have been thinking about recently regarding learning with symmetries. So some new models we've been thinking about, and also some theory of how you actually gain from invariances in various ways. So this is based on joint work with a number of people, and in particular, I would point out the lead student authors on these papers, Behrooz Tamasebi, Derek Lim, Joshua Robinson, and Sharud Gupta. Okay, so in this audience, I'm skipping all my motivation, what is symmetries and what is graph learning, etc. So I just like to have everyone on the same page. Here's like a small formal definition about learning with symmetries or invariances. So in the standard learning setup, what we have is we are given n data points and we're trying to estimate some function f hat to minimize some loss. We all know how that works. And when we want to do learning with invariances or equivariance, we additionally know that the function we are looking at has some kind of symmetries. So the symmetries in the data usually. And hence we want this f hat to be invariant or equivariant with respect to some group G. So invariance means that if I apply an action from that group to my data point, then the value of the function doesn't change. And equivariance means that if I transform my input data point, the output is transformed in a corresponding way. So this could be the same action, or it could be some corresponding action. That's why I call this G prime here. And now there's various ways how you can achieve learning with invariances. So one way to do this is to say, well, I know that f hat should have these symmetries, so I just build it into my function class. So really the only thing I can learn, I make the model such that the only thing that I can really ever learn is an invariant function or an equivariant function. And then you have to think about, well, how do we actually design such a model class, etc. And the second strategy is to say, well, I'm actually instead of putting these symmetries into the model, which requires me to think about the model architecture, let me just try to learn these symmetries from data. And then I use like standard, like generic model class, but then I have to change my loss function in some way to actually tell the model what are the symmetries that I want. So today I'll be talking about both of these approaches to different problems with different motivations. So here's the outline of my talk. So first I'll address this question of encoding symmetries. And of course, this is a big field. I'll just tell you about one example that comes from our recent work, and that relates to building equivariant neural networks on eigenvectors. And the second topic I want to talk about is to actually then change gears a bit and think about learning symmetries. So can we actually learn them? And that requires then thinking about what should be the loss function. And I'll use that with an example of actually putting more structure into the representation space of my data. And finally, I want to just give you some more theoretical insights. And this is basically the question that what maybe many of you have observed and many works have observed is that if we build a model that has symmetries built in, like an invariant model, for instance, it actually learns better. It needs less data. And that, I mean, it's very intuitive that that should be the case. It has fewer degrees of freedom. It has some prior knowledge built in. But what I want to show you is that you can actually prove this also theoretically. So this is what I'm going to talk about today. And I want to start with the models that are equivariant from the model class. And this is really motivated by the idea of processing eigenvectors. So we'll be building neural networks on eigenvectors. And first you may think, why would you ever want a neural network that takes as input an eigenvector? But there's actually many examples where this should be useful. And one example actually was mentioned in Andreas's talk yesterday, where they encoded molecules as point clouds, and then to actually bring them in a canonical position to make this equivariant to rotations, we needed PCA. And so the PCA is the eigenvectors. Other examples that are very common are, for instance, positional encodings in graph neural networks or graph transformers, Laplacians of manifolds, matrix factorization, etc., etc. So eigenvectors obviously come up in many places, and it makes sense to build neural networks on eigenvectors. So what's special about eigenvectors? Well, this is a talk about symmetries, so they do have some symmetries. And here I just want to mention the probably simplest symmetry of eigenvectors, and that is the sign flip. So the idea is that if V is an eigenvector of my matrix, then minus V is also an eigenvector. It doesn't change anything. And if you run an eigensolver to compute the eigenvectors, then you may get either V or minus V, and both of them are fine. But obviously, like if your neural network is sensitive to the sign flips in an unpredictable way, then it won't generalize very well potentially. So this has motivated the idea of building neural networks that are invariant to sign flips. So for instance, if you want to do positional encodings and graphs, that's very useful. So this was the SignNet architecture. And basically what it does is if you build a function that's a function on a set of eigenvectors. And if any of them flips their sign, the output of the function doesn't change. So the embeddings that you get are still the same. So this turns out to be very useful, for instance, for positional encodings for graph classification. So I don't want to talk about that project today. I want to talk about something slightly different. And that is to go from invariance to equivariance. So that really means that if now I take one of these eigenvectors that are input to my function and I flip the sign, the output of the function should flip accordingly. So for instance, if this is like from vectors to vectors, if I flip the sign of the first vector, like in this little picture here, then the first column of the output should flip its sign as well, and the rest should remain constant. So I can also write this in matrix form as f of vs, where v is the matrix of the eigenvectors, and s is some diagonal matrix with the sign flips, is the same as f of v times s. So this is the equivariance. Okay, so this is what we want. And the first question you may ask me is, why do you ever want a sign equivariant neural network? Why do we care about that? Other than that we can do it as an exercise, but maybe there's also some use to it. So I want to give you two concrete examples of why sign equivariance is good. And these are also examples where sign invariance, so the sign flip invariance, is not enough. It's probably not enough to actually address these problems. And the first of these problems is positional encodings from eigenvectors. So this is something that many of you are probably familiar with, is that what we often do to enhance the expressiveness of graph neural networks is to add in positional encodings for the nodes that are derived from the Laplacian eigenvectors. So these positional encodings essentially tell me something about the global position of the node in my input graph. And the same for graph transformers, you use that to essentially bring in the structure of the graph. So we use these positional encodings and they come from eigenvectors. So we have this problem that we have some neural network or a part of our neural network that works on eigenvectors. So this actually, and then using this and building like invariant eigenvector neural networks works very well if you want to do things like graph classification. But there are some applications where these are actually not as useful. And this is, for instance, if you want to do link prediction or clustering. So those tasks relate to the following question, that I have two nodes and I essentially want to know something like, are these nodes very well connected or are they part of the same component or something like that? And this is very clearly visible from the eigenvectors. This is well known that the eigenvectors give you the cluster structure of the graph. So this is what you see here in the left side of the picture. But if you do a sign invariant network, so the colors kind of depict your positional encodings here. What you get is that the nodes U1 and U2 here get exactly the same embedding. And so now if you wanted to predict whether W should link to U1 or U2, it would be basically the same probability. Whereas if you look at the graph, it's probably not the same probability. And this is actually not a coincidence. This is actually something that will happen all the time. So what will happen is that if your positional encoding function is sign invariant, then any two automorphic nodes, so that means nodes whose like neighborhoods look exactly the same, they're symmetric, you could map them one to the other, they get the same embedding. And in some cases, this is really useful because all that matters is the neighborhood structure of the nodes. And we can predict from that, and we want to generalize. But sometimes this is not what we want. And for instance, for link prediction, this is probably not what we want. You also see this in this other picture up there. This is for a texture reconstruction problem. You see that the sign invariant, like processed eigenvector is symmetric. The two ears of that cat are actually the same. So what this means is that if you do sign invariance, you actually do lose some information about the position of the node in the graph. So they give what is called a structural node embedding, but they lose some information about where exactly globally that node is and how well it is connected to some of the other nodes. Of course, if you think about it, if we want to do link prediction, what we really want is some link prediction probability that should not change with the sign flip of the eigenvectors. But the slight fine difference is that we want this link prediction, so the link probability of the link should be independent of the sign flip, but this is a function on a pair of nodes. And if we have a function on single nodes that is sign flip invariant, that's not enough. That doesn't encode the structure. So what we actually want is we want an invariant embedding of node pairs from which we can predict the link probability, for instance, but not an invariant node embedding. So that's the difference. But well, this example is here because there is solutions to this. And one solution is to say, I make the node embedding not invariant, but then from the non-invariant node embeddings, I derive this invariant node pair embedding. And one way to do this is to use sign equivariance to the rescue. So we are still aware of the symmetries, but we are not being invariant, we are being equivariant. And then we know exactly how the symmetries affect our outputs. It's not arbitrary, it's just a sign flip. So what we'll do is the following. We'll first find assign equivariant node embedding. So this is depicted on the right here, and you see that actually here the colors indicate the clusters. And then we find a decoder that takes as input 2 of these node embeddings and then decodes it into a sign invariant a pair embedding, for instance, by just taking entry best products in an MLP. So this way we can get sign invariant pair embeddings, but they're also still aware of the position. So they're actually more informative. So this is one example where sign invariance by itself is actually not getting us all the way because we're kind of stuck in the middle here of that plot. The second example I wanted to show you is building orthogonally equivariant models. So in many applications, what we care about is equivariance to rigid transformations, for instance, in physical systems. So basically what you want is that you have your input, it's a point cloud, and you shift it around, you rotate it, and it shouldn't change. So here, this is expressed actually just with the rotation. So you have some orthogonal matrix, and you multiply your x by an orthogonal matrix, and your model should be equivariant to that transformation. So this is reflection and rotation. And yesterday, Andreas mentioned a way how they are handling it with the molecules, and this is to use PCA frames. So the idea of PCA frames is that we have our point cloud and we basically find a canonical alignment of this point cloud. So we do the PCA and then we align basically the principal components with some axis. Then we process it and then we rotate it back. So this way we are actually equivariant. So this is what this R and R transpose here means. These are the eigenvectors from the PCA, the rotations. So this actually works, and this is a nice model, very useful. There's only one thing you have to be careful about with that idea, and that is that once we again take eigenvectors, we have the ambiguity of the sign flips. So again, PCA is taking eigenvectors. So the solution that is commonly used is to basically just sum over the different sign flips that we could have. So if we are in k dimensions, this is 2 to the k sign flips. And of course, now I'm showing like there's the ambiguity of the sign flips, and I'm talking about sign flip equivariance. So somewhere there should be like the connection. And so the idea is that, well, instead of summing over all the sign flips, we could just make H sign equivariant. So the H is basically this function that you apply here to your data. So you take your data, you rotate it, you do your sign flip, then you apply H, and then you rotate it back. And H is some arbitrary function. So instead, what we can do is we can make H sign equivariant, and we don't have to do the summing. And what happens is that H is sign equivariant, and then we apply H to the rotated data, and then we just rotate it back. And this basically takes care of all the sign ambiguities. And this is provably, the model that comes out is obviously well defined, and it's provably orthogonally equivariant. So you can actually do without the sign flips by putting sort of that complexity into the H. And if H is rich enough, then this actually is a universal model. So any orthogonally equivariant function can be approximated by this kind of model. Okay, so this was my second example about how sign equivariance actually helps in modeling in applications. So now with that motivation, let us look at how could we actually build a sign equivariant network. I kind of advertised now that we should care about equivariance to sign flips, but how do we actually build such a network? And so the first idea is to maybe just follow, like one of the strategies to build an equivariant model is to build a linear equivariant map, and then you just interleave it with pointwise nonlinearities, for instance. So what we have to define is what do all linear equivariant maps look like that are equivariant to sign flips. So well, it turns out that this is what it looks like. You have the formula there. It's linear functions are sign equivariant, but it doesn't actually allow any interaction between the eigenvectors that way. So this is a bit limited. So instead, what we looked at is to look at polynomials. Polynomials can approximate functions well, they're a good model. So let's look at what do like all sign equivariant polynomials look like. And so this is something you can actually analyze, and here is what they look like. So they have a specific functional form, or you can bring it into that functional form. So this has like this green part and the red part. So the red part is the invariant part. So it's some polynomial that's invariant to sign flips. And then this is an element-wise product with something that's a linear function applied to your data and another linear function. So what this model really is it has these two parts. One part is a linear part, that is the equivariant part, and then you have the invariant part. And now we can try to build this into a neural network and parameterize this polynomial essentially, or approximate it. So we will approximate this with a neural network. And the way we do this is that we already know a model for the invariant part, because I mentioned that we do know how to build a sign flip invariant neural network. This is called the SignNet, for instance. And then the rest is just a linear function. So this is actually relatively easy to build, and it directly builds on architectures that are there. So this is going to be our layer. It's basically this linear times the invariant function. Okay, now one last thing I wanted to mention is this, or two last, is this any useful? So we've built we've motivated it, we've built the architecture. So you can actually show that this kind of architecture is rich enough to approximate all sign equivariant functions. So it's basically approximating those polynomials well, and then these polynomials approximate the function. So this is actually good. It's a universal approximator. If you only care about functions from vectors to vectors and not sets of vectors to sets of vectors, this is actually simpler. You can just use the model that is here. So you can just actually build it with an MLP instead of the SignNet. This is also extendable to include permutation equivariance as well, by using the deep sets for symmetric elements framework. But then we don't yet fully know whether this is universal or not, but it's practically usable. And then you'd use the second version here. Okay, so this is for the theory. Let me show you that you can also use this in practice. So let me show you some experiments, and the experiments will be directly for my motivating examples that I talked about earlier. So the first one was the link prediction example. So here's results for link prediction on random graphs for a few different models. So the first one is just the GCN, and then the SignNet. So SignNet has this invariance problem, and you see it doesn't actually perform that well. And then there's a few ways you could do the sign equivariance. And the actual sign equivariant model that we built here performs the best, and it's also by runtime, it's actually pretty good. Okay, so this was for link prediction. And now let's look at the orthogonal equivariance. So this was the thing with the PCA frames. So here we used point clouds from to solve n-body problems. So what we did was we also generalized this to higher dimensions, so not only 3 dimensions, because these, like, the benefit that you get from not having to do the summing over the sign flips is greater with higher dimensions because it grows exponentially with the dimension. And so you see in the first plot the runtime of the sign equivariant model versus the normal frame averaging. And because the frame averaging grows exponentially in the runtime, it's of course much slower. While in terms of error, they are actually pretty much the same, the two models. So you actually do get a good gain in runtime while not losing anything in terms of error. Okay, so this is all I wanted to say for now about encoding symmetries for eigenvectors. Next, I want to switch the topic a bit and talk about learning symmetries. And we'll talk about this with the application of learning to a better representation geometry of your data. So to do this, let's actually think about representation learning more generally. So we have some unlabeled data, we train some good representation of our data, and then we like such that basically a linear readout is working pretty well. So this is something we all know, but let's think a little bit about what would actually a good representation look like. What do we actually want from this representation? So some things that we often put in is something like there should be some kind of semantics in the representation. So it should capture, of course, some semantics of the data, such that, for instance, all the dogs are together, all the cats are together, etc. So you want like globally that data points that have the same meaning are close to each other. So this is something for the global structure. And sometimes what we may also want is some local structure that also has a meaning. So for instance, if you think about word embeddings, there's the thing that I go from one word to the other, like from the country to the capital, and then like that kind of linear relationship translates to other countries and other capitals. So these so here the linear transformation essentially has a meaning too. So it's not only the global structure of the data, but it's also the local transformations that matter, that have some kind of meaning associated with them. So they correspond to maybe some specific relationship or so. So maybe like those are two examples of something desiderata that we may have when we think about representation learning, of a good representation. So what do we commonly do when we do representation learning? Of course, there's some well-known methods. Let me look at one of them. And this is contrastive learning. So what contrastive learning says is that you get these pairs of data points that are, and then you tell the model these are similar, so you should put them close to each other, and the similar ones could, for instance, come from data augmentations, or they are dissimilar, so you should put them far away from each other. So, well, if we now relate this to our goals from the slide before, this definitely does encode the global like semantic geometry of the data, thinking that the augmentation doesn't change the meaning. So basically, points that are like close in meaning should be close, are generally close together. So it does like learn the class structure in the data. For the local structure, it's at least not enforced in the objective function. So the loss function for contrastive learning just does these similar, dissimilar pairs. It doesn't actually say anything about transformations in latent space, that they should correspond to something. So maybe it emerges like by accident, but we are not actually guiding it to do that. Okay, so why could this potentially be a problem? So in fact, if you think about it, like in contrastive learning, you take these augmentations of the data and you essentially ideally map them into the same point in latent space. So this means you're actually completely forgetting about, say, data augmentations. So, so if we think about this, there's that's of course, it has some advantages in terms of robustness, but it also loses information. And that's why, like, it has been observed that actually sometimes it's maybe better to have approximate invariance rather than full invariance. Because let's say we wanted to decode the color from these images or so, or have like something that, some fine-grained classification that actually relies very heavily on the coloring of the animal or so. So it's actually good to be sensitive to augmentations to some extent, in a local way maybe. We still want the global structure of like cats being separated from dogs, but maybe we do want to keep a little bit of the information. So how could we achieve this? And so one way to achieve this is to say, okay, I go away from the invariance and maybe I'm okay with approximate invariance instead. So all the cats are still close, but they're not exactly in the same location. But instead, I'm trying to somehow encode those transformations of the data. I don't want to completely forget about them. I want to encode them in some way locally. And one way to do this is to go from invariance to equivariance. So what equivariance here means is A of x is a transformation and augmentation of the data. If I transform my data in point in input space, there's some kind of corresponding transformation in embedding space. So this is the TA. and that kind of encodes that augmentation. So this has been done in some recent works. And the way this is done is that they say, okay, we learned the TA. So this is one way to do it, to basically have an additional part of your network. So you have the global invariance, and then for the local equivariance, you basically have some MLP that encodes this transformation on the latent space. And then you just train basically the output of that MLP to be close to the embedding of the transformed data point. So this actually works. It does help you to remember some of these augmentations. So you actually, it helps to, you can see, you can actually decode the augmentations from it, for instance. So it does help to keep that information. It's still not perfect. There's still some issues with this. And so one is that, I mean, issues compared to like what I said I would like to have. So one issue is that TA is, the transformation is actually not linear. So linear transformation can be very good because it's actually directly, it's much simpler and it's directly predictable. And the other thing is that this can be inconsistent with composition. So if I do two augmentations to my data point, so I rotate it and I clip it or something, and then the transformation corresponding to the concatenated augmentation is not the same as if I would concatenate the transformations. So this is something that's maybe also not so desirable. So let us think a little bit about how we could address those blue points of maybe going from the MLP to some encoding that's more linear, easier to read out, and it is consistent with compositions. Okay, so this leads us to the following goals for models to think about. So the first thing I wanted is that the latent space transformation should be linear. So this means I do some augmentation in my input space, and then I want that to correspond to a linear transformation in the embedding space. And the second thing I'd like is that I want this to be compatible with contrastive learning. So ideally, since contrastive learning works with pairs of data, I would like this to work with pairs of data too, so that I can just kind of plug it in and combine it with contrastive learning in this case. So how are we going to do this? So if you think about contrastive learning, we get these similar pairs of data points. And now they actually already give us some kind of augmentation. I mean, one is like they're augmented versions of each other. And so I want that like their embeddings have a linear relationship in the embedding space. And the embedding space here is a hypersphere. In contrastive learning, we always normalize, so we are on a hypersphere. So a good linear transformation on the hypersphere would be an orthogonal transformation. So basically what this would mean essentially is that I take my image, I do an augmentation, and then the embedding space, this augmentation corresponds to some rotation. And now different augmentations correspond to different rotations. So this is kind of the main idea. This is a simple linear operation in the embedding space. We'll try to keep it local. And now we have to see, is it possible to learn such a thing by just looking at pairs? Okay, so let's see how we could do this. So what we want now is that a change of the input, like a transformation, input transformation corresponds to a rotation in embedding space. So we have to somehow like enforce that rotation somehow in our embedding. And so, well, how could we describe a rotation? One idea is that if I take two vectors and I rotate them, that preserves actually their inner product. So you think about the angle between the vectors, you rotate them, the angle is the same. So if their angle remains the same, that's actually an indication that this is that transformation was a rotation, if I transform both the same way. So this is the motivation for the following loss function. that we're actually, so what does this do? You see there's like two terms I'm comparing here. The one is the second one is the inner product between the embeddings of data points x and x prime. And the first one is the inner product of the embeddings between their augmented versions. So what this really does is it looks at the inner product between these two vectors, and then I augment both of the input data points, and I look at the corresponding embeddings after augmentation, and they should have the same inner product. So they basically have been transformed in an analogous way. And this is achievable with a rotation if the augmentation actually corresponds to a rotation, because rotations preserve these inner products. So this is what we are going to penalize. The question is, can I maybe satisfy this thing in other ways as well? Maybe it's true that I could achieve it with a rotation, but does it necessarily like enforce a rotation? So how well does it, how closely does this objective actually correspond to a rotation? So does it actually mean rotational equivariance? So what the following proposition says is that this is actually true. So the proposition says the following, that if my equivariance loss is 0, that means if my augmentations preserve angles, so the augmentations are embeddings, then there exists an orthogonal matrix such that that orthogonal matrix encodes that augmentation. So for each augmentation, I'll have a different matrix, but I'll have the same matrix for all the data points. So that means, and the other direction is kind of easy. If such a matrix exists, we can make that loss 0. But if the loss is 0, that means such a matrix exists. So there's actually an if and only if. And the same thing also holds approximately if the loss is not really 0, as it may be in practice, but it's close enough to 0. So you basically can show that this like encoding via rotation holds approximately true. So this is nice. So this tells me that, okay, this relatively simple loss that also just works with pairs of data points, that actually helps me in finding potentially geometry that like where the rotations, so the rotations correspond to the augmentations in the data. So this is good. Now I want to also think about the second part that I had kind of brought up with the MLP approach. And this is that the composition. So if I have two augmentations that I apply in sequence, ideally I would like the transformation, the corresponding transformation in embedding space to be also just two rotations that I concatenate. So basically a product of these rotations. And what this corollary says is that under some conditions, this is actually the case. So this row of A is just the matrix that the rotation matrix that corresponds to the augmentation A. So the augmentation, the transformation corresponding to the composition of the augmentations is the same as the product of their corresponding matrices. So this is actually then consistent with respect to compositions. And what this actually means in terms of groups, if you think about it in groups, that this row that basically takes my augmentation and finds a corresponding rotation matrix, this defines a group action. This row is actually finding a group action. So what this actually means is that I'm viewing my augmentations as a group, and I'm encoding that group of augmentations via rotation matrices or orthogonal matrices more generally. So is this even possible? Like theoretically, maybe this is like not even possible. And this is actually, there's some theory that says that if your augmentations are a Lie group, that this is actually possible and you can encode it via orthogonal matrices. Okay, so this looks good. So we have this loss and we see that actually has some good theoretical properties. And I basically use these rotations to encode my transformation. So I want to just show you that this idea actually can be used more generally. And so basically the key idea here is to get my pairwise loss that helps me get the rotations is the following, that I can actually characterize the rotations by the fact that they preserve inner products. This is kind of where we started out from. is that basically any matrix that leaves inner products untouched for all x, that's a rotation matrix. And from that, I could build my logs. That was like my motivation also. So the same thing actually also works for some other groups. So for instance, the Lorentz group, which is related to hyperbolic spaces, you can define it in a similar way by not using the inner product, but the Minkowski inner product. So there's other groups that you can define in this way. So this actually generalizes this idea that I just talked about to other spaces. Now, we talked about this equivariance loss, and now I would just want to kind of finalize the loss and just like fix some other issues that may arise. So one is the issue that, well, I said I want an equivariant embedding, but in principle, if I would map all my data to the same point, that's also an equivariant embedding. It preserves all the angles, but it's of course not very useful. So we want to kind of really enforce the model to also still spread out the data. And we can do this by adding a uniformity loss, basically something that like encourages the spread of the data. And the second point is that I talked about this local equivariance, and that is something that we wanted to add because it was missing maybe from contrastive learning, but we still want the global invariance, so the global like global encoding of semantic meaning, and that like your augmentations, because they don't change the meaning, they shouldn't lead to like arbitrarily large changes in embedding space. And so to preserve that global structure, we'll also add some invariance back in. And so this uniformity plus invariance loss together is basically the info NCE loss from contrastive learning. So the final loss that I'll actually be using in my experiments is a combination of the info NCE loss and the equivariance loss that I just talked about. Okay, so let me just show you some empirical results related to this. And mostly I want to demonstrate to you sort of that this loss function actually gives you some rotations. It actually learns rotations. So the first, so the rotational equivariance. So the first thing I want to look at here is point clouds. So we can describe proteins as point clouds. And then we can rotate these point clouds and see how do the embeddings change. Are they like changing roughly like by rotating also, or are they doing something crazy? And what we did for this is we just took the two principal components of the embeddings and just plotted the trajectories of the rotations. And you see this here compared for different models. And the first one is the CARE model that does the rotational equivariance of the embedding space, and the others don't actually specifically enforce them. SymClear is just contrastive learning. Then we have the invariance and the uniformity loss. And then we have Equimod, which is an equivariant contrastive learning model, but it doesn't do the rotational equivariance by loss. And you see actually putting the rotational equivariance in the loss really helps in at least approximating that circle in 2D. Likewise, this embedding that we obtained here is also the best at predicting the first principal component, which is an equivariant task, then because the principal component rotates with a point cloud. The second experiment looks at the following question, is that I said, okay, we want to kind of preserve information that augmentation corresponds to some rotation. But I also want this to be the same rotation for all data points, because I don't want a different rotation for each data point for the same augmentation. I want this to be consistent across the data points. So what this tries to look at is that if I would take a set of data points and I augment them in the same way, I would like the change in embedding space to be the same rotation. And does that actually hold true? So we are looking at basically finding a single rotation matrix that best approximates the change from original to augmented, embedding of the augmented data. And then we look at the error. And so if the error is very high, then that means there's no single rotation that can actually tell you how the data points change from non-augmented to augmented. And so here actually putting the rotational equivariance in the loss really helps in being able to find a single rotation matrix that encodes that change, that transformation. Okay, and just another brief comment is that you can also encode equivariance by invariance. And to kind of measure how much of your equivariance is actually just due to invariance, you can basically take a ratio of equivariance to invariance. And if that ratio is high, so this is a loss, that means you're very good at invariance, and you're basically kind of doing equivariance by invariance. And if we look at this ratio for the CARE method versus SymClear, SymClear obviously does invariance. SymClear, it has a decent equivariance too, but it actually achieves a lot of this via invariance. So it has actually a much higher relative rotational equivariance. So CARE actually really achieves it by local equivariance. SymClear is kind of more the invariance. And so one final illustration here is that this just shows that these embeddings that we got actually are sensitive to augmentation. So this is the example of color augmentation. If we make a query that's actually the augmentation and it's all more yellow, SymClear is not really, that's the middle one. The nearest neighbors are actually not very sensitive to the color, versus the CARE model does give you some more yellowish flowers. If we use another equivariant model that is not doesn't have the rotational equivariance, these flowers are also more yellow, but they already go into even more red. So it's kind of overshooting a little bit here. Okay, so and in the last few minutes, after talking about some models and sort of the modeling and empirical benefits of symmetries, let me just tell you about one theoretical result that kind of supports the good learning performance of learning with symmetries more generally. So this is really the question that in practice, we see that learning with invariances works better, but in theory, the question is, can we actually prove that it needs less data to learn? And so I want to go now to prove this from the setting of neural networks to just kernel regression, and because it's a bit simpler to analyze. So we look at kernel learning, and we'll actually do kernel learning more generally on some manifold. And we know our target function is invariant. So here we're just looking at invariance. So we are looking at specifically an estimator that's invariant as well. So we are learning an invariant function. And the question is now, how do we gain in sample complexity? There are some previous results on this. And basically what they say is roughly this, that effectively it is as if you had size of the group more times more samples than you actually have. So if you think about, for instance, of permutations, that means that if I observe one set, I have essentially observed all the permutations of this set too, because they have the same label. So this is the size of the group, is the number, this number of transformations that I can do. So these results hold for finite groups and isometric actions and on spheres. This is the paper from Alberto Biatti. And what we do in our work is we actually show that the same thing holds for arbitrary groups. In particular, you can get such a result of reduction of sample complexity also for infinite groups. And we can do it for arbitrary manifolds and not only on spheres. So here is the result in a nutshell. So what you see here is the classical sample complexity bound. It says basically that the risk is bounded by some term that depends, it's something divided by n. N is the number of samples, and then the green part is sort of the complexity of the space, your manifold, and then the dimension comes in the red part, and S is something related to the smoothness of the function. So it's exponential in the dimension. And what we get, and here the second thing here is what we get when we have invariance. So the thing that changes is the green and the red parts here, the highlighted parts. And that so there's two changes basically that happen. The first one in the green part this is the volume of the quotient space. The quotient space means that you look at your data and you do basically all transformations of a data that happen with that group that you're invariant to. So for instance, all permutations of your set or so. And all of these basically essentially are now collapsed into, well, one orbit is that collection of those transformations. And now the quotient space is the collection of those orbits. So this is now just the complexity of that compressed space. And for finite groups, this often looks like just the previous term divided by the size of the group. And now, since you're dividing by the size of the groups, it's as if I had multiplied my number of samples and by the size of the group. And the second part, this holds for infinite groups. And basically, the dimensionality here is reduced by the dimension of the group. So this is, for instance, if you have rotations, this is an infinite group. So there's a dimension that comes in. So this is something that's new compared to previous work. They actually didn't have the infinite groups in there. This bound is also tied up to constants. Now let me just show you how this would translate to some examples. For instance, if you have permutation invariance for sets, it's essentially as if I had observed n times m factorial samples if I had m elements. And the same would hold for graphs where node embeddings are permutation invariant. It's basically the same thing. If we look at sign flip invariance, we have with m eigenvectors, we have 2 to the m sign flips. So we get an improvement of the sample complexity samples by 2 to the m. And for shifts, such as like convolutions, we get like an m square for m by m images. Finally, if we look at point clouds, where we have invariance to translation, permutation, and rotation, we get a gain both in essentially the effective number of samples by m factorial, like the permutations, and we get the gain from the infinite group. And this is essentially the dimension here in 3 dimensions of for the rotations. So it's like 3m minus 6 instead of 3m. Okay, so how do you actually prove this? I'll just give you the main idea, not the full proof, it's too much. So basically, the sample complexity depends on some complexity of the function space that you have. And we will measure this complexity of the function space by sort of the number of eigenvectors of the Laplace-Beltrami operator. Think of it as the Laplacian of your manifold. And so we look at basically how many of these we would be using. That's kind of the complexity, the dimension of your space. And so to give you an intuition, if we had the sphere, these basis functions would be the sines and cosines. And then let's put an invariance. This would be maybe the reflection about the y-axis. And what you get from that is that, well, basically, if we want to be invariant to this flip about the y-axis, basically you want symmetric functions that look the same on both sides, so flipped. So you want only basically the even functions here. So this basically removes half of your basis functions, and this removing half of the basis functions is essentially the gain that you're getting here. So the gain you could measure by essentially how many of these eigenvectors of that operator are actually correspond to the symmetries that you have. They have the symmetries that you want. And the others that don't have the symmetries, you're not allowed to use them anymore. So those basis vectors essentially you throw away. So the ratio between the symmetric and non-symmetric on general basis vectors. How do you count them? How do I know how many like eigenvectors does my like operator have here that are like in the reasonable range of eigenvalues? This is essentially the non-trivial part. And so in general, this is counted by something that's called Weyl's law. But this Weyl's law really only holds on manifolds. And what we needed is actually on this quotient space, because we only look at these invariances for the invariant functions. So this is basically the complications that this quotient space is not necessarily a manifold. And now you have to work around that to prove basically a corresponding result for the quotient space. So you what we do is we take, instead of like this full, so the quotient space, you can think of it, it may not even be connected. It's like some pieces here and there. We take the biggest piece, and then we have to take care of the fact that this may have a boundary. So what would happen here in my example? So you have to take care of that as well, because this Weil's law only holds for manifolds that don't have a boundary. So once you have done all of that, you can actually prove that result, which gives you this gain in sample complexity. So with that, I'll just stop. I hope I have shown you some examples of how symmetries help in making models more robust, more efficient, more effective, both in theory and in practice. There's, of course, many open questions. I'll just leave them here out on the slide. And thank you. I'm open for questions.
Yeah, thank you very much. I think now we don't have any questions. Let me check whether we... Yeah, so from the audience, if you have any questions, please ask them, post them, for example, in the Slack channel, or there's a Q&A button you can use in the Zoom. Vinci, do you have any questions?
Yeah, I think I can ask a question. Thanks for the wonderful talk, Professor Stephanie. And my question is actually, I think it's pretty nice that you encode this local linear transformation into the representation of the data. But it seems like you specify as rotation, but have you thought of the other augmentation form?
So we don't say what rotation it is, has to be some rotation. But you mean, should it be something else than a rotation?
Yeah, for the other, because right now you feel like it seems like in the local minimum, maybe around the local minimum, you have different types of rotations close to it, and you consider them somehow as the similar mode. And how about the other augmentations?
Oh, right. Yeah. So basically, each augmentation would correspond to a different rotation, basically a different direction of rotation. We don't specify which one corresponds to which. We only specify that it should be a rotation. And this is mostly because when you think about the hypersphere, like the linear operations there is kind of like mostly rotations. And they should be close. So like each augmentation will correspond to a different rotation. Once you have a new augmentation, you'd have to learn that different rotation, of course. You can generalize it to other spaces with a similar reasoning. Like there's other examples where you can use that pairwise, something like an inner product thing.
I see. Yeah. I think, yeah, a quick question following up this is like, you mentioned there's a global closeness where contrastive are already done, and also this local linear transformation, where I'm curious in general, like, yeah, of course, there are a lot of things in between where how do you define two images are close to each other? Of course, you can define some similarity kernel that do contrastive learning, but have you thought of any idea to use some other technique or equivariance or symmetry to capture like which mode should be put, maybe one close to the other, automatically learned?
So this is more about the global arrangement, that whatever, should the cats be close to the dogs or close to the cows or something like that. Yeah. We haven't thought about that. That would, like, if you want to do it in a fully unsupervised manner, you probably have to decide on some criterion of what should be like, the measure of similarity or so. So right now, this what I described doesn't really address that global arrangement. Maybe it would happen like somehow implicitly, but there's no way like we actually enforce it globally. That's a good question. So yeah, it's maybe what you then want is more like an actual similarity between classes, or a more graded like similarity or so. This would be like a general problem with contrastive learning, that you could like help it arrange it like a bit better, right? I don't know of any approach that could do this easily without actually looking at the data, but there is maybe something.
Thank you.
Yeah, thank you. And I think we have a question from the audience. Have you looked at the towards representation alignment and uniformity paper for the alignment on the sphere of the laws that you defined?
Okay. So basically, we take the alignment on uniformity directly from the contrastive laws, from the Wang and Isola idea of like decomposing that alignment and uniformity. You could, I don't know what exactly that other paper is about. You could possibly use other terms as well here. So this is just to basically have the global invariance, etc., and to spread out the data points. But you could possibly like the actual, like if we were in lots, you could actually combine it with other terms as well.
Oh yeah, it further said that the loss very much looks like a Lie bracket. Is there any connection?
So I mean, the loss has actually a lot of connections in that, like a little bit what I showed you was the idea of I didn't call like the stabilizers. So the rotations are essentially defined via these inner products, and that's kind of where the loss comes from. So there are a lot of connections here with like where this comes from and like what it actually means, rather than like, okay, this is like this like idea of preserving angles is actually deeper than what it looks, maybe.
All right, yeah, I think we are time is up, and thank you again for the amazing talk, Stephanie. I think I should also learn a lot from your talk. Before we conclude, is there any questions so far, or if there's no questions, then let's finish this session. And thank you again for giving us an amazing talk, Professor Stephanie. And yeah, and we are now entering our second phase of today's agenda. It's the oral presentation. Let me hand over to Ke-Xin. Is Ke-Xin here? Hi, Ke-Xin.
All right. Yeah, I will introduce all the speakers for the papers for the oral session today. So the first speaker is Donald Loveland, and the paper is about on performance discrepancies across local homophily levels in graph neural networks. Donald, are you here? Can unmute. Okay, that's good.
Oh, because you have to make the presenter as the one of the co-hosts, because
Oh, is it?
there we have a Zoom bomb, so we disable this functionality.
I see. Okay, thanks. Doing that right now.
Yeah, once you promote the presenter as the co-host, they should be able to unmute themselves.
Okay. How do you make them co-host?
Oh, let me make you the host.
Oh, I see. Oh, I see.
Yeah, now you should have see the option now.
Okay. I think Donald, now you're able to speak.
Yeah.
Awesome.
Yes.
Great.
Thank
The
you.
floor is yours.
Okay. All right. And is that showing up correctly?
We don't see any slides. We're seeing the loading screen.
Yeah, let me. Okay. Okay, let's see. That works.
Still no. Maybe you can try
Okay.
to either download it, or you can also try. Yeah, I mean
Yeah.
the current one so it works fine.
Okay, sorry, I'll stop sharing for just 1 second.
Yeah, no worries.
Okay, let's see if that does the job. Okay, yeah, so we will. There we go. Does that work now?
Yeah, it's perfect.
Okay, great. Thank you. Hi, everyone. My name is Donald Loveland. I am a PhD student at the University of Michigan in Ann Arbor, and I'm excited to give an overview of our recent work on performance discrepancies across local homophily levels in graph neural networks, a slightly long-worded title that I hope to unpack in the next 15 minutes. So to start off with, to kind of get everybody on the same page of the setting that we're thinking about, we're primarily operating under node classification, where obviously the goal is to assign classes to nodes. And of course, we want to try to synthesize both the features and neighborhood structure information in the network. So here I have a little toy example where we want to try to predict the class of the gray node. And of course, we want to use the ego node feature vector as well as the neighboring feature vectors and synthesize this information. Node classification pops up in quite a few applications. And specifically, we try to think about applications that impact individuals. If we think about financial systems, we can imagine scenarios where we might be trying to assess credit risk or recommend new lines of credit. And additionally, we see the use of these node classification algorithms in social media, content recommendation, group affiliation, or assignment. And so we want to make sure that when we go to use these graph representation learning paradigms, that they are working well. And what we end up finding in some cases is that the structure information that we're actually trying to leverage may not actually help performance. And this is sort of problematic because then what's the point of actually using these paradigms? And one of the things that have become very prevalent in the last year or two in regards to network structure is this idea of homophily and heterophily, where homophily is this tendency for nodes of similar properties to connect. Sort of the idiom that you sometimes hear is birds of a feather flock together. And this is something that was assumed quite often in sort of benchmark data sets that papers were using. And it ended up reinforcing a lot of the development of GNN architectures. And then once these data sets with heterophily started picking up, which are data sets with nodes where nodes of differing properties connect to one another, we started to see a pretty massive decline in our performance. And we want to try to build models that can hopefully operate in both regimes. As the field has continued to develop, we need metrics to be able to talk about homophily. And so one of the common ways that we do that is through this global homophily ratio. Here I'm using an edge variant of that. And ultimately, this is a simple calculation of trying to capture the ratio of edges which are homophilous in a network. So again, edges that connect nodes of similar properties. And we just divide that by the total number of edges. And as this metric is higher, we have graphs of pure homophily. And as this metric is lower, we have graphs of pure heterophily. Now, as with any global metric that we take, ultimately, we are sort of condensing down a lot of information into a single metric. And a problem that we were curious about with regards to this global homophily ratio is whether this has any impact on information loss as we start to think about these prediction tasks. In particular, we wanted to think about the local perspective of node classification, in particular with this idea of homophily. Sort of our concern was that if we have this global homophily ratio, there's a chance that we're failing to capture nuances in the local mixing patterns and sort of just prioritizing sort of the majority mixing pattern that occurs. And so this can lead to individuals potentially getting lost in the aggregation procedure, particularly when they're underrepresented. And so if we sort of think about the ramifications of what might happen in these cases, if we go back to our financial systems, there might be cases of elevated perceived risk solely by, us being unaware that these nodes that look different than the majority exist in the network. And so sort of the rooting question that we're going to carry through this presentation is sort of how does this node level homophily relate to an individual node's performance? And can we use that node level homophily to essentially infer if we'll be able to properly or adequately predict for a single node? To be able to do this, we obviously need to have some sort of localized metric to talk about local homophily. So in this, we're going to use the local homophily ratio, which is a pretty simple extension where we're now just going to look at a localized neighborhood around a particular node. So now we have homophily ratios for every node T in the network. Here I have it written using the one-hop neighborhood. And in the paper, we show that, this does not necessarily need to be the case. But what we generally find is that if you make this too big, depending on the properties of the network, you sort of just lose any sort of individual distinctiveness across the nodes. So if there is signal sort of within the local neighborhood, we want to try to exploit that. And once we make this perspective switch to a localized, to a local homophily ratio, we can then start to talk about things like the local homophily distribution, which is now sort of a more expressive way to talk about the global homophily information rather than just the single global homophily metric, which is what has been historically used when analyzing these data sets. And if we take some of the data sets that we actually use as our common benchmarks, we can see that while they do look globally heterophilous and homophilous, sort of what would be alluded to by the global homophily ratio, we also see that there are these interesting skews that emerge. And more importantly, what these skews will end up doing is skewing the training data that we end up using. And so the question is that, for nodes that are far away from sort of these majority regions, is anything going to happen to them at test time when we have this skew in the training distribution? So this leads us to our research questions, where we ultimately want to think about this local homophily distribution and try to understand, one, does the local homophily distribution have any impact, sort of the identification question of the problem? And then we take a sort of model-centric approach and try to understand if there are certain model designs that exacerbate this issue, and if there are any model designs that can help alleviate this issue, help sort of promote more generalization across the local homophily range. So for the contributions of this work that I'll go through briefly, we start with some light theory that tries to understand essentially the connection between the local homophily ratio and a test node's predictions. We then propose a modification of a preferential attachment model that allows us to essentially intervene in the attachment process and essentially induce over or under representation in the local homophily distribution. And then finally, we have some empirical analysis where we use both the graph generator and some real world data sets and show ultimately how these discrepancies arise. So the analysis setup and maybe the picture I want you to keep in your mind throughout this is shown here, where effectively we want to characterize how a node's local homophily level is going to impact performance, specifically relative to the global homophily level of the entire graph. And so for our analysis, we parameterize this through this alpha t, which is effectively the shift that the test node is going to have relative to the global homophily value. And so when it's further, or when it's a higher number, we're further away from the global homophily ratio. And so for our theoretical analysis, again, we want to try to build this relationship between the two. And so we start by looking at two linearized GNN architectures that adopt some of the common paradigms we see in this homophily, heterophily learning settings. And we develop closed form solutions for the weight matrices. Really where the core assumption comes in that sort of limits the theoretical analysis is that we have to assume all the training nodes have the same local homophily ratio, which we do relax obviously in our empirical setting, but this sort of gives us the intuition of what would happen if we had a heavily biased training set. So the two things that we primarily look at are these aggregation functions. And so I'm going to refer to these as sort of homophilous and heterophilous aggregation. And this is commonly what's been seen in the literature to help promote sort of globally better GNNs, but these haven't been looked at from this local perspective. So for the homophilous aggregation, this is sort of your traditional weighted average or weighted sum. And then for the heterophilous aggregation, we're looking at this concatenation operation where we separate the ego node from the neighboring nodes. And ultimately what we're able to do through this is come up with this kind of clean closed form solution of what the prediction for a particular test node is going to look like. And this ends up looking like a sum of the correct label for that node plus what we refer to as this deviation term. And there's some math that ends up working out in the paper where effectively this deviation term always pushes you away from the correct label. But what we want to focus on here are sort of these coefficients on the two. And the idea is that depending on the magnitude of these coefficients, we're going to get lesser or greater deviation. And so I have the two coefficients right here that, again, in the paper, we do some analysis on. But for this presentation, I want to focus on the difference in their magnitudes, because intuitively, if we have larger magnitude coefficients, that's ultimately going to lead to larger discrepancies later on. And so what we do here is we look at the two parameters that these coefficients depend on, the global homophily level H and the degree. And what we ultimately see is that for the majority of cases, this B het, or the coefficient on the heterophilous aggregation, ends up being much more common in this plot. And it ultimately displays significantly smaller magnitudes compared to the homophilous coefficient. And so what this generally tells us is that if we adopt this concatenation aggregation, we can hopefully alleviate the discrepancies that might arise if we were to use something like a homophilous aggregation. So think like your GCN architecture. And so with that, to try to generalize the theoretical setting a little bit more, we start with a synthetic analysis where we're going to take our preferential attachment model and make some modifications to it. So for the classic kind of preferential attachment model people use in this homophily analysis, ultimately it's a two-step process where we sample some label and generate a feature associated with that label, often some sort of like 2D Gaussian or n-dimensional Gaussian. And then we have the connection addition step where we build a compatibility matrix that essentially tells us, given a particular homophily ratio, how likely we are to connect to either nodes that look like us or nodes that don't look like us. The thing that we add is we add this intervention step where we effectively can turn off the compatibility matrix and inject a random new homophily ratio. And why this is valuable is it essentially allows us to interpolate between effectively a uniform distribution of homophily ratios and something that's very, very tightly peaked that you would find in the classic preferential attachment model. And so as we increase this probability and modulate this parameter, we can sort of induce more or less skew in our models, or in our graphs that we're studying. And so to actually study how this ends up creating discrepancies in the GNNs that we're using, we begin by stratifying the nodes in the test set after training based off of their local homophily ratio, and then compute their performances across these levels. And we do this first row-wise for different global homophily ratios. And then we also do this for a handful of different models. Here I only have 3, but we have a ton more in the paper. And kind of the point I want to make is that on the left, GCN is going to adopt something similar to theorem 1, which is the homophilous setting. And GCNII here is going to adopt something that is more related to the second theorem. And what we end up seeing is that, one, they do all experience some sort of degradation relative to this local homophily ratio, except obviously the MLP, because that doesn't use the graph structure. But as we start to take sort of pairwise differences between them, what we also notice is that often the GCNII, or the heterophilous design model, ends up performing significantly better in regions further from the global homophily ratio. And so this is another indication that even under more complex settings, we do get this model design does help. And then lastly, I'll go quickly through some real world analysis. Here, it's a very similar plot. I've just converged all the models onto the same plot. And what you'll have is a gray bar, which denotes the range where the global homophily ratio falls. And then essentially, as you move away from that gray bar, you are increasing the distance of the local homophily ratio. And pretty much as we look across all these data sets, irrespective of the original global homophily ratio, we see that there are these degradation patterns. I think the results are a little less clear in terms of the individual models. When we do our pairwise analysis, we see that it does generally follow it, but there are a lot of extra designs in here that we don't necessarily look at in the theory that could be contributing to these different patterns. So with that, I'll leave with some conclusions. We started with identifying this relationship between local homophily and performance, and I think kind of more importantly, also with the global homophily sort of conditioning this information. Then we theoretically and empirically demonstrated how being underrepresented in regard to this local homophily ratio can essentially cause degradation at test time. And then we offer some alleviation in regards to the aggregation mechanism that one might adopt. And I do want to point out that these mechanisms do exist, but I think the point that we're trying to make here is that, you know, this is now a sort of new way to understand sort of when we get performance increase with these models, sort of who is the performance increase helping? Is it helping everybody uniformly, or is it helping particular groups? And so we hope that this helps to kind of answer that question. So yeah, I will end it there. And I do have some future work that I'm happy to discuss if anybody has questions or anything. So thank you.
Thank you, Donald. Yeah, for the audience, if you have any questions, please post it right now. I think we have time, a bit over time, but I think we can have one questions, maybe.
And also happy to answer over Slack after too.
Yeah, definitely. Cool. I don't think there's any right now, but I think we can defer this question to the Slack channel. Yeah, thank you for the great.
Thank you.
Yep. All right. Next up we have Francisco. You here? Yes. Okay.
Yes.
Yeah. Here. Okay. Yes, I can hear you. So Francisco will talk about his recent work on Metapath learning for multi-relational graph neural networks. The floor is yours.
Thank you. Do you see my screen, right?
Yes, I can see it.
Perfect. Thank you very much. Thank you for the introduction. So I'm Francisco, and I'm presenting this work that is a collaboration between University of Trento in Italy and University of Aalborg in Denmark. So it's called Metapath Learning for Multi-Relational Graph Neural Networks. So let's start with a brief introduction to end motivation of this work. So here you see a very simple example of an heterogeneous graph that is very helpful to understand later on how our method works, right? So we have different node types here. So we have actor nodes that are pentagons. We have movie nodes and director nodes, right? And some nodes, so movie and director nodes, might have some features depending on the color. So for example, a movie node can be a drama or a comedy node, depending on the darkness of the blue. And a director can be an award-winning or a not award-winning director, depending on the yellow or the orange color. Of course, then we have different relation types. So for example, an actor can be a main actor in a particular movie. Again, an actor can be appeared in a particular movie. Then a movie can be directed by some specific director, and at the end, eventually, a movie can inspire some director, of course. Last but not least, some nodes, in this case actors, have a label which can be positive or negative, depending on a specific metapath. So here a metapath is a specific sequence of relation types. In this case, red relation with so from a pentagon, so from an actor to a blue movie, so a comedy movie with a red relation, and the movie then have a purple relation with an award-winning director. So all the nodes that have this particular path, they are labeled as a positive node. So for example, A here, and all the others that have a label, so all the other actor nodes are negative because they don't have such a path. So the idea here is that we want to learn such metapath, measuring the potential informativeness of each relation type in the graph. So we want to score each relation and to learn such path in order to, let's say, explain the prediction, so the positive label of the target nodes. So here you see a very simple, here you see the main modules of our approach, which are two, so the scoring function and the Metapath graph neural network. The scoring function has the goal of scoring each relation type in the graph, starting from the target nodes. And in order to give the best scoring relation to the graph to create this candidate metapath that is given to the Metapath graph neural network, that has the goal of predicting the targets of the levels of the target nodes by using one relation type for each layer of the graph neural network. So if we have a metapath made by two relations, we will have a metapath graph neural network made by two graph neural network layers, in each layer we only consider one relation type. We propagate the message only through one relation type. So we can go through the scoring function, starting from the first iteration of the scoring function. in which the idea is that we want to predict the labels of the target nodes, which are A, B, and C in this case. So we consider the two graphs separately. So the first one with relation red and the second one with relation green, which were relations main actor in for the red one and appeared in for the green one. So we need to score this relation, but how do you score them? The idea here is to use a graph neural a neural network. So with some parameters that we want to learn that is able to give at the end a score. Okay, yes. How do we make predictions? Essentially, as you see on the left, we give a weight to each of the children nodes that in this case are node D, node E, F, G, and H, and these weights are used to make predictions on the parent nodes that are A, B, and C. So using the max operation, so we take the max weight between the children and we predict so that we can predict the label of the target. So the score is the mean squared error loss between the predictions and the target and the two labels of the targets, and we want to minimize this loss, this score, learning the parameters, of course. So at the end, we will have these parameters that are should be around 0 or around 1, whether they are correctly learned, of course. So we will have a score for relation red, a score for relation green, and then we can say that the weight for the red relation better explains the labels of the target nodes A, B, and C. And so the red relation is the first one added to the current metapath. And at this point, we should give this current metapath that is made only by one relation type to the graph neural network that propagate the message only through this relation type in order to make the classification. But then we need to go back to the scoring function in order to check whether we should add a new relation type to the metapath. And how we do that? Essentially, we are in this situation in which we know that red relation is a correct one. We have the labels on the targets, and we need to propagate these labels, creating some pseudo labels on the children nodes that in the next iteration, so in the second one, become target nodes. And this is how we essentially do that. So we propagate these labels, creating some bag of nodes in this way. Essentially, whether a child node is, whether some children node have a common parent that is positive and they do not have any negative parent, they stay together in a positive bag, like node D and node E. They only have one parent node that is positive, which is node A, and so they stay together in a positive bag. All other nodes stay in a negative single node bag. In this way, we have propagated the labels of the previous nodes, and now we can make predictions on these bags of nodes in the same way as before. So now we have that from movie nodes, the relations are the purple and the pink one, and we do the exact same thing as before. So we try to minimize this the score function. We try to minimize the mean squared error between the predictions and the target and the two labels. And by learning some weights. And in this case, the difference with respect to the first iteration is that when we predict the labels of the bag of nodes, we use as children all the children of all the nodes inside the bag. So we used node M and node L as they are children of the same bag because they are children both of node D and node E. So at the end, we have a score for relation purple and a score for relation pink. And in this case, you see that the learned weight for the purple relation better explains the true labels of the target bag of nodes. And so relation purple is the next one that we can add to the metapath that now is made by relation red and relation purple. And now we can give this metapath to the metapath graph neural network, predicting the labels of the target nodes, so A, B, and C again. As I explained before, now in each layer of the graph neural network, we use we propagate the message only through one relation type. So in the first layer, since the best relation was the red one, we propagate the message to the red relation, and in the second one to the purple relation. And so that we can update in this way the node representation. So the node representation on the bottom left, the update is simply the graph neural network update, in which we only consider one relation type for each layer of the network. Just for simplicity, I explain the approach for one metapath, but we used it with multiple metapaths. We set a max number of metapaths, and this is how we combine the representation of a node from different metapaths. So essentially, we concatenated the embeddings from different metapaths for a single node in order to make update his representation. So then we can go to the let's say results, starting from the research question and the competitors of this work. So the first research question was whether our approach can recover the current metapath when the number of candidate relation increases. So in a setting in which we increase the complexity of the graph in terms of number of different relation types. So for this, we created 16 synthetic datasets, so synthetic heterogeneous graphs, where the number of relation types increases in order to make them more complex. And for this, we also selected one single metapath that can label the nodes that we want to predict. For the second research question, we want to know whether our approach was competitive with existing approaches in real-world datasets where the number of relation types is small. And for the last research question, we want to know whether our approach outperforms existing literature, let's say, in real-world datasets where the number of relation types is high, so such as in knowledge graphs. On the right here, you can see which are the competitors that you, of course, find also on the paper, that essentially have in common one thing, that they create the node representation by employing message passing through all the relation types in the heterogeneous, in the multi-relational graphs, but in different ways. So, for example, some of them use attention mechanism, others use different weights for different relation types, sharing weights in the layers only to the same relation type. But really the common thing is that they still use all the relations in each layer of the network. So let's start from the first research question. Here you see that in each matrix we have one method. Ours is the last one, MPGNN, and in each cell of the matrix we have one synthetic dataset. Going on the right or going on down, we increase the complexity of the graph, as I said before, like increasing the number of relation types in the graph. You see that our approach with respect to the others is better in terms of F1 score, and also can recover all the time the single correct metapath. And we also created the synthetic datasets. And here we have 4 different synthetic datasets where we increase both the number of relation types, so the complexity, and also the length of the correct metapath. So we tried with length 2, 3, and 4. And our approach is, let's say, the most consistent across all these different settings with respect to the competitors. For research question 2, instead, we tried with very common and used datasets in this heterogeneous graph learning, which are DBLP, ACM, and YAMDB, which are 2 of them are all of them are heterogeneous graphs where the number of relation types is small, as you see in the third column. So we have few relation types, and as you see from the results here, again we have the F1. And our approach is really comparable, has similar results with respect to the competitors in this case. So we are happy with that, also because competitors had very good results on these datasets. That's it. And last but not least, for search question 3, we tried our approach in the freebase dataset, where the number of relation types is high. So this dataset is freebase, and we have 237 relation types. But we, in order to create these 10 rows, which are different, which are 10 tasks, we extracted one relation for each of them that becomes a sort of feature that we want to classify. So here, in each, as you see from the third column, the number of relation types is 236 because one of them is used as in order to be classified. And as you see from here, our approach, so MPGNN can have better results with respect to the competitors we tried, but in 8 out of 10 tasks on Freebase, but also on the tasks in which we are in which we, let's say, lose, we are really comparable with the best between the other competitors. So we are also happy with this result. And so my presentation is finished. Thank you very much for your attention. If you have any questions, doubts, or I would be happy to answer.
Well, thanks for the great talk, Francisco.
Thank you.
And let's see if there's any question in the Slack channel. Yeah, I think people will probably post some questions in the Slack channel later. So if you can do that, that would be great. Yeah, but it's super interesting. Oh, actually, one question.
Thank you.
Does this scale to much larger graphs?
Well, we tried with this freebase, which is well, the complexity here is not related to the number of nodes, but more on the number of relation types in the graph. Because essentially the idea is that we want this Metapath graph neural network that prunes that only use one relation type in each layer. So essentially we are pruning the computational graph, right? So yes, it can scale to larger graph because the score function consider each relation separately, so can give a score to each of them separately, and then the MPGNN can simply aggregate information using one relation type for each layer. So yes, I guess it absolutely can scale.
Awesome. I think there's another person typing, so yeah, I think we still have 3 minutes. Maybe we can finish. So maybe we can wait for
yes, of course,
for this person to finish typing. Yeah. Okay, so actually I have 2 questions. First one is the approach generic or just in case of the entities mentioned?
Of the, sorry?
Is the approach generic or just in case of the entities mentioned?
Well, generic in the sense that it can be applied to different knowledge graphs. The important thing is here is that they should have different relation types. So this is the only let's say constraint that we need for the graph, because we need to select the best relation each time. So yes, that's the only constraint that I see here.
I see. Cool. And another question is, are the used data sets are the used data sets synthetic in the initial set of experiments?
Yes, exactly. Here for this slide and for the next one, we created these are 16 synthetic data sets, one for each cell of these matrices, and essentially we designed one correct metapath so that we have the labels, and then we increase the complexity of the graph adding new relation types.
I see. That makes sense. And I think one last question is, how is the scaling on the relation types? So if you have a graph that has like 1,000 relation types, would that be realistic?
Well, actually, I think that it cannot really not be really a problem in the sense that again we our method select one relation each time, so we are really trying to it is really trying to prune the computational graph with the graph neural network, and with the score we are simply selecting the best relation. Another thing that I want to mention is the fact that the scoring function can of course go parallel, because we can evaluate different relation types in parallel, because of course the score for relation red doesn't have any implication for the score of the green relation, for example. So they can really go parallel as we do in our code. So it is also quite, let's say, fast in this way.
Awesome. Great. I think thanks for the great answers. I think that's all the questions for now.
Thank you very much.
Cool. Thanks for the great talk.
Thank you.
Next up, we have Joseph.
Hi.
Hi, Joseph. So Joseph will talk about work on representing edge flows on graph via sparse cell complexes.
Yes, all right. Thank you very much. So welcome to representing edge flows on graphs via sparse cell complexes. First of all, I want to give you some motivation on edge flows, how we can represent them using cell complexes, and then take you on a journey diving into the problem and the solution we came up with. So first of all, why do we even look at these edge flows? Well, on many graphs, on many networks that we have, we can observe flows on the edges between, for example, between intersections. You can count the number of cars or the number of passengers on a train, between two stations. You can have calls between different cells of cell phones, data flowing through a computer, or the internet network, or even power that is transferred between substations and power plants. And a problem we have with this data, if we observe it, is that it's very complex and it's hard to interpret it, and that it's noisy, and that we kind of want to process it. And so what we can do, I want to give you a bit of an intuition from the continuous case, is we can use the Helmholtz decomposition. If you're not familiar with it, I will explain it just a bit. So what you can do is you can decompose this vector field, for example, into gradient flows, which are kind of a potential function, and then flows flow from high points to low points, if you want to think about it like that. And then what's left is the solenoidal or rotational or curl flows. And there we again have this problem of interpreting these flows. And ideally, what we would want is we want to decompose this again into a few significant, interesting, interpretable flows, and some noise that we don't really care about because it's relatively small and we can basically ignore it. And so the two tasks that we set in this paper is mainly the denoising of these flows, and secondly, if we can, to find some structure that is hopefully meaningful. Investigating how meaningful the structure is a bit hard. I will talk a bit more about that in the end. What can we do on graphs? Well, in the continuous case, the equivalent to the Helmholtz decomposition used by topological signal processing is the Hodge decomposition, where you can decompose the edge flows into first the gradient flow, which is induced by a potential function on the nodes. So, for example, think of a resistor network. You have different electrical potentials, and then you have a current that flows between them. And then what we need is some higher order structure. So if you're familiar with cell complexes, we have some two cells that we add, similar to two simplices, but more general if you know simplicial complexes, or if you don't know anything, any of these concepts at all, just think of these as some circular flows. So a polygon, and there are flows around these edges. And we can assign a float value to each of these cycles. And if we then sum these up, we get the curl flows. So flows explained by a small number of cycles with some detected flow on them. And then what remains is the harmonic flow. And in this case, so the harmonic flow is high dimensional. And in this case, we assume the harmonic flow to be the noise, or the kind of left leftover components of the flow that we do not explain in this paper, or that we would remove for the task of denoising the data. Then, if we look at the problem definition quickly, just to be sure that we're all on the same page, given some edge flows that we have, we want to find such two cells that explain the flow, or if you don't know them, cycles or polygons, such that the loss is minimized. And the loss is just the least squares of the harmonic flow. So we want the harmonic flow to be as small as possible. And we have also shown in the paper that the decision variant of this problem is NP-hard. Therefore, we need an approximation algorithm to find a solution in a time that is useful to us, that is not too long. This approximation algorithm on a high level, it starts with the flows. First of all, projects them into the harmonic space. So in the beginning, this just removes the gradient flows, and all of the kind of circular flows still exist. And then with these harmonic flows, we try to approximate these in multiple steps. First of all, we look for a small number of suitable cell candidates, so possible cells or possible cycles that we could add to the graph to explain these flows. Then we evaluate these candidates by calculating the loss, so projecting the flows into the harmonic space that would be the result of adding each of these cells, so individual different losses. And then we simply add the best candidate, so the candidate that results in the smallest loss after adding it. And then we return to the beginning, where we again project it into the now updated harmonic space. So of course, some of these flows are now not harmonic anymore, but are now part of the curl space, part of the explained flows. And therefore, this reveals some new patterns that can then be approximated in the next iteration. And then we just greedily add more and more cells until we are done. What does done mean? Well, either we have added a certain number of cells, so maybe we want to add the 20 most significant cells, then after 20 cells we will terminate, or if the loss is below a certain value. So for example, if we would say, okay, we want to bring the loss below 1, then we would terminate after adding this one cell, at least in this example, because the loss is now, as you can see in the bottom, 0.44. Of course, these are just arbitrary examples. And the question is, how can we find good candidates, and how can we find them in a time-efficient manner? Previously, there has been similar work on these cell complexes where we had predefined cells. So if we have a way to select some cells that we think might be good to explain these flows, then we can supply them to the algorithm. And while this, of course, works, and this showed that this decomposition is useful, in general, this makes it more difficult to use the approach. Another approach used triangles as two cells. The number of triangles is somewhat manageable, even though it's relatively large. And therefore, you can calculate the flows on all these triangles and just try out all the triangles. And if you're familiar with algebraic topology, you'll recognize that this means we are kind of a special case of the cell complex, which is a simplicial complex, where all the two cells have to be triangles. But of course, this limits the applicability. Apart from being less efficient, if you have an actual square, for example, many networks don't even contain triangles. So for example, a grid-like road network contains virtually 0 triangles. So this is not an approach that is universally applicable to all networks. If we try to generalize this all triangles approach to cell complex, we would kind of have to look at all cycles. But since there are exponentially many, this is not feasible. Instead, we need a heuristic. So first, let's talk about what this heuristic needs. First of all, it needs to consider all of the harmonic space in an intuitive sense. Since all edges can have relevant flows, we need to consider all edges in this as a simplified explanation. Secondly, since there are exponentially many cycles, this heuristic must not consider all cycles, otherwise its runtime will also be exponential. And a good start for this is a cycle basis. If you're not familiar with algebraic topology or topological signal processing, a cycle basis is a set of cycles, a set of polygons that spans the entire harmonic space, so that includes all the edges if you were to take the union of these cycles. the size of the cycle basis is linear in the number of edges. So it's the number of edges minus number of nodes plus 1. And for sparsity, we cannot just take an arbitrary cycle basis, but we need to find a kind of good cycle basis, because if we only find cycles that are very bad at approximating the flows, then we need to add very many cells in order to reach a low loss. So we need to find some cycles that are very useful or very have a very high flow on them with regard to the flows that we have sampled before. How can we construct such a heuristic? Well, in order to get a cycle basis, we can just start with a spanning tree. So a spanning tree on the graph, on any graph, will induce a cycle basis simply if you take all the edges that you removed and combine them with the path through the spanning tree. So in this example, you can see that we induce a cycle basis consisting of the triangle and the square. And if we do this and calculate all of these cycles in the cycle basis, we already bring the complexity down from exponential in the number of nodes to number of nodes times number of edges, which is at least approximately asymptotically the same as considering all triangles. So this is already a relatively good approximation, but a relatively good time complexity. But we can get even better if we use some nice properties of spanning trees. So we can take an arbitrary root of the spanning tree. It doesn't matter what node this is. And if we then want to calculate, for example, the complete flow around the edges of one induced cycle, so intuitively, a good cell would be a cell that has as high as possible a flow around its edges. Instead of manually walking along the cycle and calculate and summing up all the flows that we encounter, we can instead once for the whole spanning tree, calculate the sum of the flows from the root to each node. This takes asymptotically the number of nodes time. And if we then want to calculate the flow on the path between two nodes, we can just take the difference between these two nodes, because then the path from the root to the lowest common ancestor of these two nodes will cancel out in the sum. And in the end, we are very efficient with this. So what we need, the time complexity of this is now no longer nodes times number of nodes times number of edges, but it's now almost linear in the number of edges, plus of course the time it takes to find a spanning tree, which well at the state of the paper, it's still edges times logarithm of the number of edges. I think we can get this down to linear in the number of edges, but since I have not thought that completely through, please don't quote me on that. I may post an update somewhere if I figure it out. And so we have a quite good runtime. We have also tried this to evaluate this empirically. So we have two different heuristics to find these spanning trees that then result in two different heuristics to find cell candidates. Unfortunately, I don't have time to go into this detail anymore. But as you can see, the runtime is almost linear in the number of nodes. Side note on this synthetic graph that we used, the number of edges is also linear in the number of nodes. So what's actually important is the number of edges. But we've also tested on real-world data, where we've seen a much better, approximation with the same dimension of the curl space compared to the previous approach, which was using all triangles. For example, here in the traffic flow network of Anaheim. So we've shown in conclusion that this algorithm works. So just to recap it quickly, we have generalized methodology in topological signal processing, depending on what previous work you look at, either from triangles to polygons or from pre-selected candidates to a heuristic selection of candidates. So we have reduced, in this case, the requirements for the input of the algorithm. And it is an efficient approximation algorithm for this NP-hard problem. It's an iterative greedy algorithm utilizing spanning trees, and it worked quite well, as I'm happy to report in empirical experiments. For the future, we would like to look at other downstream tasks to kind of assess the usefulness of these cells for other tasks. And there may be some ways to adopt core ideas of this paper to other contexts where we are also dealing with edge flows, also dealing with cell complexes, and which I do not have the required domain knowledge for, do not know anybody who can interpret these cells on real-world data effectively, it would be very nice to do a qualitative evaluation of the inferred cells. So on synthetic data, the algorithm was able to recover cells with an acceptable accuracy, I would say. But of course, this doesn't say anything about the real-world applicability. You can find the full paper or the PyPI package on the under the link that you can see in the QR code, or you can go to my website, hoppe.io, like my last name, where you can also find all those links. Thank you.
Great. Thank you, Joseph. Let's see if there's any questions. I don't see any for now, but yeah, definitely stay in touch on the oral discussion channel in the Slack. And
yeah, I mean, I'd be happy to periodically monitor the oral discussion channel if you have any questions, or you can write me an email, or write on Slack directly, or whatever you prefer.
Sounds good. Yeah. All right. Thank you so much for the great talk today. Good.
All right. Thank you.
Thank you. Yeah, I think that's the last oral talk for today. So thank you all for attending. And I think that's also the last session for today. So stay tuned for the tomorrow. And there's exciting oral sessions and the keynote, and also